Allison right now, so hopefully you guys are seeing her on the screen. How come you guys did not immediately jump to her?
Mine jumped.
Mine's not issues.
Okay, well, it shows that you're presenting, so hopefully that's the format. So PV equals nRT includes all the four variables of gases that we typically use: pressure, volume, moles, and temperature. Now I'm going to show you, remind you of a couple things on this. One, the R, it is a very specific R. It has units of liter, atmospheres, moles, and Kelvin, right? So it's 0.08206 latmas per molix. If you're taking a look in my notes, you guys might want to turn to where it says snapshot versus before and after, and it kind of walks you through in my notes. You might want to show the front page. You have my notes with you there, Allison, since you're not broadcasting. Okay, so take a look at the R right there, 0.08206 latmas per molic. That is really important. Guys, you got to focus. This is a pretty challenging class. But that determines what the units are in that PV equals nRT problem. So if they ever give you any other pressure in any other units other than atmospheres, you're going to have to convert them. Now, the reason I'm putting that formula up there is not because I want you to do some plug and chug problems. And the reality is I could give you those. But I'm going to point out a couple of things here that actually lead to other laws. Now, what is the relationship right now between volume and moles? They're directly proportional. Can you write V equals, and then write the letter A and then N? Okay. And I want you to do me a favor. Can you circle all of the variables, like make a big circle around the P and then the R and the T, skipping the V and the N? No, they have to be part of one circle.
Oh.
So just take the top portion of it and then just run it together. Okay. So would you acknowledge if I say that volume is directly proportional to the moles, that is only true if pressure and temperature are held constant? I'm gonna say it again. The only way we can ever compare any two variables is if they're being held, the rest of the variables are being held constant. So see that little A right there? That is some constant that represents all the other values. So why is that a big deal? Because that volume being directly proportional to moles means that we can use volume in the place of moles in some cases. Let's do another one here. Would you agree with me that pressure is also directly proportional to moles? Can you do another P equals AN? Are you with me on this? Now, how does this work? Well, let's write an equation on the board, and I'm going to show you how we can start using these variables to help us out. So why don't you slide your computer over a little bit more to the right? And let's do the equation. H2 plus O2 goes to H2O. And can you put the subscript of gas, G, next to each one of those? Well, that pen's starting to die too, isn't it? Oh, actually, that's going to be a G as well in this particular example. Now, normally, now watch. I'm making this problem where we're having the hydrogen and the oxygen turn into water as a gas. The reason I'm not making turn into water as a liquid is because, do you realize that we cannot apply any gas laws to a liquid? Are you with me on this? So if they ever ask you, hey, what's the volume or what's the pressure of this, and it's a liquid, that problem is an invalid question. Now, what I want to share with you, and by the way, that is not balanced, is it? No. And we can't, you're just having issues. I've like watched 2 or 3 of them just dribble down. You got it now? Okay. At least like maybe put them close to your mouth when you try to eat them, or I don't know. Now, if we read this here, put your finger on the first 2. Doesn't it say 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2? Oh, right? Agree? But if we hold all the variables constant, would you agree with me that the volume is directly proportional? Goes sit back to the V equals AN. Okay, see that V equals AN? That means that the volume is directly proportional to the moles. So if everything else is held constant, that includes the pressure and the temperature and obviously the R, then instead of reading my equation in terms of moles, I can read that equation in terms of any unit of volume I want to. So what I could say is I could say for every 2 liters of H2 that react with 1 liter of oxygen, I'm going to get 2 liters of H2O. Are you with me? Now, what if I gave you this? I'm going to give you this is the recipe is that recipe right there. But what if I gave you these 2 quantities of H2 and O2? Let's say I gave you 500 milliliters of H2 and 100 milliliters of O2. And I asked you how many milliliters of H2O are formed. Yeah.
O2 is your limiting reactant.
Now, you can tell us immediately, right? But the reason we can is because, and I should have made a disclaimer. In this particular problem, the pressure and the temperature are being held constant. Because if that's not the case, then we cannot use the coefficients in terms of units. But see how, in this case, I have my volume units are milliliters. So couldn't I say this, that for every 2 milliliters of H2, I'd react with 1 milliliter of O2 and get 2 milliliters of H2O? Because milliliters, aren't they just 1,000 times smaller than a liter? So couldn't I use any prefixed liter unit to then solve this equation? Now, I like what you said here. You said that we have to figure out the limiting reactant first. Now, this is really easy because I have 500 milliliters of H2 and 100 milliliters of O2. Let's make this just for fun. Can you change that 100 milliliters to 200 milliliters?
What about moles, though?
That's what I'm saying, is that normally this would be an equation written in moles, right? But if I tell you that the pressure and the temperature are constant, see that formula V is equal to AN? That means that volume is directly proportional to N times whatever the constant is of all the things being held. So since they're directly proportional, I can use volume in the place of N. Does that make sense?
Yeah.
So in this particular case here, you know how we'd actually figure out the limiting reactant? Can we go 500 divided by the 2 for the coefficient? Wouldn't that give us 250? Yes. And then couldn't we do 200 divided by 1? Wouldn't that give us 200? And whatever one's smaller, wouldn't that be our limiting reactant? It's exactly the same as how we do it with moles. Why is that important? Because if we know that 200 milliliters of O2 is my limiting reactant, then couldn't I use the ratio between O2 and H2O to figure out, well, if I have 200 milliliters of O2, wouldn't I then need 400, or wouldn't I get 400 milliliters of H2O?
Yeah.
Does that make sense to you?
Wait. By 200 milliliters of O. Then you could draw a table like that.
So if you could literally do this way. Could you write? Let's do a table. Could you write 200 milliliters O2 on the top part of the table? So we're going to use milliliters to do exactly what we used to do with moles, right? So couldn't we then go, hey, for every 1 milliliter of O2, wouldn't we get 2 milliliters of H2O? If the equation was written in liters, could we do the same thing for liters? Or if it was written in picoliters, or if it was written in megaliters, the formula works. And so that wouldn't this be multiplying the 200 by 2 and dividing by 1? Wouldn't that give us 400 milliliters of H2O?
Yes.
Now, can I make this a disclaimer? This only works because everything involved in this equation is in gas. I'm sorry, yeah, or gases. If one of those, if O2 is a liquid or a solid, we can't compare them that way. We'd have to convert them to moles.
So the actual limiting reactant,
Nope, the actual limiting reactant is O2.
But I thought that it just...
Right, 400 milliliters of H2O. So put your finger on O2, up above in the equation. We determine that that's the limiting reactant, right? Based on the ratio of 2 to 1 between hydrogen and oxygen, right? We have 500 milliliters of H2 and we have 200 milliliters of O2. O2 is my limiting reactant. Are you having trouble figuring what the limiting reactant is?
I mean, like, yeah, that makes sense, but if it produces like 400 milliliters of H2O.
Right, but if we'd used H2, it would have produced 500 milliliters of H2O. This is a 2 to 2 ratio. And the problem is that 100 milliliters of that H2O, of the H2 is not going to be used. So if we were to use H2 as our limiting reactant, right? Would you agree with me? Can you put your finger on the 500 milliliters? Okay, if that's my limiting reactant, isn't it a 2 to 2 ratio with H2O?
Yes. Yeah.
See the coefficient in front of H2 and the coefficient in front of H2O? Okay, that would mean that I should get 500 milliliters of H2O, right? The problem is that I don't have enough oxygen to completely react with the H2, so that's pretending like I'm going to get an extra 100 milliliters past what I would normally get. So the 200 milliliters of O2 will produce 400 milliliters of the H2O, which is less than what H2 would have produced, which would have been 500.
All right, so we shouldn't have divided it.
No, the divided by 2 is just our trick way of figuring out what the limiting reactant is. Remember we did it with moles? Remember how we go like divide by the coefficient and whatever is the smallest? You guys remember us doing this last year? We did it last class or a few classes back as well. So that divide by 2 and divide by 1, that's just our trick way of figuring out the limiting reactant. And then once we have the limiting reactant, we must use the limiting reactant for the rest of the problem. Yeah? Okay. So just pause, and I'm not going to do this as well. But in this case, mustn't the disclaimer have been that pressure and temperature were held constant?
Yes.
Now, would you agree with me in a different problem, if I held the volume and the temperature constant, couldn't I give you this problem? And instead of giving you 500 milliliters, couldn't I give you, could you erase the 500 milliliters above and the 200 milliliters? Could I instead give you atmospheres of both of them?
Yes.
Or torrs of both of them? Or millimeters of mercury of both of them?
Yes.
So couldn't I have gone like 5 atmospheres of H2 reacts with 10 atmospheres of O2. How many atmospheres of H2O? And isn't it the same principle, except now we're just using, we have to find the limiting reactant, which in this case would be, what would the limiting reactant be here, Allison? It'd be H2, right? Because it's a 2-to-1 ratio. And if you want to do the quick way, we divide 5 by 2 and get 2.5. We divide 10 by 1 and we get 10. So my limiting reactant must be H2, right? Again, that's a trick way of doing it. Then we go 2 moles of H2 for every 2 moles of H2O. And we go, oh, if I start with 5 moles of H2, I must end up with 5 atmospheres of H2. I'll end up with 5. So I only wanted to show you that because occasionally they may throw a problem where you're like, what the heck? They've given us no information to solve for moles, and that's because they've given you hidden information that says, oh, by the way, you could use it this way. Yes, Ashley.
If you're given other units of like pressure, let's say 4 kilopascals, would you have to convert to
No, because the ratio is still the same.
Okay.
Isn't the ratio 760 millimeters of mercury for every 1 atmosphere?
Yes.
So if I had 2 atmospheres, wouldn't it be double that? Just like 2 would be double 1. So yeah, the ratios still hold. Are you with me so far? Now, can you do me a favor here? I only show you that because how often will you see a problem like this? Very rarely. But what if? What if you end up seeing something where they just don't give you enough information, and all they give, if they just give you liters and they ask you how many liters of the product are formed, you've got to be able to use the coefficients as liter ratios. So I want to jump really quickly to a few other pieces of information they give you that it's kind of helpful. Can you guys open up or go a little bit down below to STP? I'm going to switch over to my screen briefly. My notes. The way I'm going to talk about my notes today is going to be my notes versus the other notes. I'll put it on my screen here, since I know that some of you guys do not have this. Yeah. Okay. So this is. I don't think I'm broadcasting my screen, so I'm going to go back to me. And I'm going to go to screen share. And you're going to see like the dizzying array of stuff. Make it stop. Okay, so if you take a look at this right now, I want to point out a couple pieces of information. I don't know if you can see on your screen. Can you see my screen now popping up? And you can see my little arrow. So STP is a piece of information they're going to give you often that kind of gives us an idea. What's that? 273 and 1. And what that stands for is standard temperature and pressure. They'll sometimes say, instead of standard temperature and pressure, they'll say standard conditions, just because they want to zig when you're zagging, right? But this is hidden information. So if they say that my gas is under standard conditions, then that means 273 Kelvin and 1 atmosphere. So that is helpful to us because it's information that we aren't given in a problem. Secondly, this piece of information right here, where it says 1 mole of any ideal gas has a volume of 22.42 liters, That's a hidden piece of information that will allow you to very quickly solve for the number of liters per moles that you have in a problem.
So is any gas an ideal gas?
Every gas that we're going to be working with, we're going to pretend that they are ideal gases. Yes.
So we can just all say that 30 liters.
No, not ideal gas. All are ideal gases. Only at STP, I might have misspoken. Only at STP is 1 mole of a gas equal to 22.4 liters. If you have a temperature other than 273 and other than 1 atmosphere pressure, this does not work.
Right, yeah.
That make sense? All with me?
Yeah.
Now, I will say this, and I don't want to spend any more time with this, but yet I do. Can you guys go to the? Can you go to the page 5 of Not My Notes?
Page 5.
Mm-hmm. And I want you to look at. You should still see on my screen right here. I want you to go to this problem, exercise 5, right now. On your own. I want you to solve for that. I'm gonna give you a minute or two to do it on your own. If you could try and tackle it on the board, that would be great as well. Actually, take it back. I don't want you to do 5 right now. I want you to do 6. I'll come back to 5. I'll come back to 5. Sorry, that's a terrible way to do this lecture-wise, but I want you to do 6 first. I'll come back to 5 in a second.
What's the constant rate? 1.08202?
For gas constant R, 0.08206. 0.08206 liter atmospheres per mole Kelvin.
In Celsius, conversion 273.15.
You got it. So I'm switching over the screen to Allison is working out the problem on the board. Isn't this a straightforward problem where they give you the pressure, the volume, and the temperature? Now, can I reiterate? Can you ever use Celsius in a gas problem?
No, we use Kelvin.
Always have to convert to Kelvin. And the bigger number, we typically use 273, but 273.15 K is actually the number. So it gives us a little more significant figures if we want them, 273.15. And then isn't it just a matter of solving for N, which is moles?
So you put the RTU.
Mm-hmm.
Or under.
Now,
It's 0.57.
And okay, it gives you 0 Celsius, but whenever you convert it to Kelvin, it's 0.5 decibels.
3. So watch, if I have 0 Celsius, right? 0 Celsius, if I add 273 to it,
Oh.
the 3 is going to line up with the 0, and it's going to be cut off right here. So the 273 just becomes our new number.
Yeah.
We wouldn't go 273 point, because did they say 0.0?
But there's only 2 6 6. No.
They just said 0.
Yeah.
Yeah. So then, and then that works that way. Yeah. Okay. Allison, can you just scoot to the side so we can see what you did?
Yeah. So is it 0.15?
It should be 0.1, or it should be 2 significant figures, simply because in the 1.5 we use 2 significant figures. So that's the correct answer. Yeah. Okay. Now I'm going to show you something here that is a variation and a way that we can work through the Pivnert law to figure out something else, and it can sometimes be really, really tricky. So I'm going to show you this here. If you turn to my notes again, at the bottom of the snapshot, and I'm going to start presenting my screen again, and I'm going to go down here to my notes. Okay. Okay. So one of the things they often ask you to solve for is they'll ask you to solve for molar mass of something. So listen carefully if you would. Do you realize that molar mass is always grams divided by moles of something? Agree?
Yeah.
Listen carefully. What they could do in a problem, they do this often, is they'll say, hey, we have a certain number of grams of compound X. We do not know what that gas is. It's a gas. And then they give you a bunch of information: pressure, volume, and temperature. If I give you pressure, volume, and temperature, what's the only other variable I'm lacking? Moles. So if I give you pressure, volume, and temperature, couldn't you figure out the moles of that particular gas? Now, if I know the moles of that particular gas, and they give me the grams, couldn't I go grams divided by moles? And wouldn't that tell me the molar mass of that particular gas? So if ever in a problem, they give you a way to solve for moles, and then they give you the grams of it on the side, or if they give you a way to solve for grams and they give you the moles on the side, you can divide grams by moles and it'll give you the molar mass. And then they'll often ask you therefore after that, go, which gas must this be? And if you know the molar mass of the gas, can't you relook back at the table and figure it out?
Are we always going to have a periodic table?
Always, always. Even on the sections where they don't want you to be using your calculator, you'll still have a periodic table with you. Now, I want to show you something here because I'm going to walk you through, and if you're a mathophile, you're going to love this. I'm going to walk you through molar mass and density and how that works together. Now, I'm going to walk briefly through this. If you want to spend a little more time looking how they did substitutions, that may help you. But there's one final equation that I want you to look at. So first of all, would you agree with me that molar mass is equal to grams per mole? Agree? And if we rearrange molar mass, we get moles, which the symbol is N, is equal to grams divided by molar mass, and grams is a unit of mass, so we could substitute M for grams. So we say that moles is equal to mass divided by molar mass. That's just rearrangement of the molar mass equation. Now, if we go back to our Pivnert problem, isn't there an N right here? If we take this N up here, which is mass divided by molar mass, we can substitute it in. Do you see how I took the N right here, and in parentheses I subbed in the M divided by MM? Which, by the way, if I have M divided by MM on the top, isn't that the same as M with MM on the bottom? Are you with me? So I'm just doing some equation manipulations. Now, we don't deal with density that often, but do you realize that density is mass over volume? Yeah. So see where it says M on the top and volume here on the bottom? We can take the M and the V and we can substitute D in there for it. So we end up with DRT over MM. And if we want to isolate P by itself, can't we switch the MM and the P with each other? Now, this formula is the way that we can get to molar mass from a density problem. Now, if I didn't have this formula, you could figure out how to get to the molar mass if they gave you the density of something, but it'd be really, really tricky. Now, when I learned this, they taught me molar mass for when you're dealing with the gas law, molar mass is equal to dirty P. Molar mass is equal to dirty P, DRT over P. Now, perhaps a more gentle version of this is the one that the other teacher whose notes I borrowed on this used. And they actually said this instead. Let me see if I can find it here. No, that's horrifying in so many different ways. Okay, watch. They did this right here. His example, if you take a look on I'm assuming you guys can see my screen. He said, molar mass kitty cat, all good cats put dirt over their pee, DRT over pee. Courtney, yep, but you'll thank me later. So however you want to remember it, it's dirty pee. Okay, now I want you really quickly to solve this problem right here, exercise 14. Solve exercise 14.
On our packet, which
Using dirty
packet?
pee.
And obviously, I'm setting you up to use the dirty P formula, but can I make a suggestion here or ask you to remind yourself of something? Would you agree with me that density units matter?
Yeah.
Isn't density grams, or isn't that mass per volume? But isn't our mass in grams usually? But can our volume be milliliters or liters or some other unit?
No.
Or centimeters cubed? Here's the problem. Doesn't PV equals nRT or a Pivner problem, doesn't it have R in it? What is the unit for volume that R has in it?
Oh, ATM times L divided by.
But what is the volume unit in that whole thing? Isn't it liters? So if it's in liters, then you have to make sure that your density is in per liter. That makes sense?
So density is equal to the volume? So we could use.
No. We're plugging into the molar mass equals dirty P.
So
But I'm telling you, the density that we use has to be in grams per liter. It cannot be in grams per milliliter, or grams per centimeter cubed, which they often will give us.
You guys, what's R?
0.08206,
Oh, dirty T.
0.08206 liter atmospheres per mole Kelvin.
0.08.
Suppressing.
0.08206 liter atmospheres per mole Kelvin. Okay, I'm assuming that you guys plugged into the molar mass is equal to dirty P. And I'm hoping that it becomes second nature that you must convert out of Celsius, yeah?
Yeah.
So they give you the molar mass, by the way. What gas, by the way, do you think that is?
Honestly, no idea. Not
32
around any
grams
degree
per
on the
mole.
table.
Is it O2?
Has to be O2. Now, you could look, I would immediately look at the noble gases, right? And if I look at the noble gas, I'll see if there's one that is 32, but there's not. And then I look at which ones are diatomic. Remember we said that Brinkelhoff all exist as pairs. Not so much. It really, you're right. Sulfur would not be a gas, or else sulfur could be our choice there. Any questions on this? Okay, let me show you one more thing. Can you turn to my notes? And I want to remind you of how we deal with before and after problems, because we're going to see problems like this quite often. And this is the formula right here. You should see it in my, I'm assuming I'm still screen broadcasting for you guys.
Wait, what was the answer? Oh, are the answers?
The answers are in the black right next to it. So that way you can check your work. I like this handout a lot.
I do too.
Very helpful. Now, anytime that you have a gas and one of its characteristics, and you guys see me, can you see the cursor when I'm circling around this or no?
Yeah.
Or is it, okay. So anytime you have a gas and one of its characteristics changes or more of them change, you're not dealing with P equals nRT anymore. You're dealing with this equation, P1V1 over N1T1 equals P2V2 over N2T2. In actuality, it's PV over nRT equals PV equals nRT, but R is a constant, right? And if you have a constant on two different sides of an equation, don't they cancel out? They don't matter. Additionally, let me share this with you. We like using this combined gas law because rarely we have to use all 8 variables or 7 variables. Now, in truth, couldn't they give you 7 of the 8?
Yes. But
And you solve for the 8?
Get them out of there.
Anytime there's a constant, we can get rid of them. Now, they typically, it'll be pretty clear what the constant is. Or they'll say something like, it's in a solid container. Solid containers tend to not expand or contract, right? Occasionally, we get lazy as question writers, and we'll just exclude a variable that we just have as constant. So if you're missing a variable and you're like, and it's volume or something like that, chances are you're not going to necessarily have to, yeah. So do you realize that we can rearrange this equation a bunch of different ways, depending on what we hold constant? And that's how we come up with the 3 different gas laws. In all 3 of these gas laws, all we're doing is we're holding different things constant. And in all the gas laws, we hold mass constant. Mass, isn't that akin or analogous to moles? That's the amount. So essentially, we're holding the moles constant in each case. Do you have Austin? Do you have a computer you're looking at or no?
It's not working. It's like you're joining your own class.
But you have to click the email link, not the link that was in the folder. I gave you a link in the email. Sorry. That should allow you to join in. Okay. Any questions here? You will often have problems anytime that they say, hey, the new gas volume is blah, or they give you some sort of switch. We know that we're dealing with the combined gas law. Now, I'm going to shift over to something that causes a lot of problems for students occasionally, and that's partial pressure. Now, partial pressure is actually not hard, but it confuses us because partial tends to indicate part of, right? And so when they say, give me the partial pressure of oxygen, we typically think, oh, that's part of the pressure of oxygen. But what that means is this. If let's say we have 3 different gases, right?
Yeah.
All 3 of those gases, won't they be contributing to the pressure in a container? So if I ask you, what is the partial pressure of oxygen, if oxygen is one of those gases, what that's really is saying is, tell me the pressure of oxygen, because oxygen makes up part of the overall pressure.
Would
Yes,
it feel like
it's very close to that. It's analogous to that, very close. So another way of saying this would be like this. Let's say I had so Kenna, Austin, and I don't know if I want another person in this or not. Oh, okay, Leo. Okay, the 3 of you.
leap him out of this?
All right, so here's what we did. I made you honorary gas particles, right? And so what I had you do, so you end up looking like one of those things they put in front of a dealership where you just kind of flow back and forth. I'm not gonna lie. I will watch one of those for quite a while. I'm gonna say. Now,
Have you ever gone and danced on them before? I have.
oh, anyway,
That was a joke.
I'm not sure how to respond to that. Those of you listening to this later. Okay, now watch. If I had these 3 gases, so let's say I had the Kenna gas, and I'm like, all right, Kenna, I want you to run into that wall. And on that wall, don't do it. On that wall, we have a kind of like in swim where they have that sensor that measures like when you touch. We have a pressure sensor.
Oh, is this the story where like you had that football player who?
No, I'm not doing that one again. No. So, Kenna, in case you're having trouble dealing with this, bounds into this now, and then she'd come back this direction and she'd bounce into this wall over here. Except you can't move out of direction; you have to go in a straight line. So you just. Okay, so for those of you who can't see this at home, she's actually reenacting this. Now, Austin, I'll save your dignity, although I do appreciate Kenna you doing this. If I had Austin run into the wall and then I had Leo run into the wall, would you agree with me that the 3 different particles are going to hit the wall probably with different pressure? Right? Now, particularly if let's say I had Austin run at full speed, Kenna run at a pleasant, whatever, like automobile. What do they call those things? What do they call this? The
Car wash thingamabobs.
Anyway, and then Leo is walking it. Leo, as we often know, does a power walk. So he's doing that thing where he does his hip shifting. Now, if I were to ask you ever, hey, how much pressure altogether did the 3 of them provide? Wouldn't you just go, well, wouldn't we add the pressure of Kenna, Austin, and Leo together? And wouldn't that give us our total pressure?
Yes,
And if I were to say, well, what was the partial pressure of Kenna? Wouldn't we say that whatever her pressure was is part of the overall pressure? So that's why if you write on the board, can you write P1, T1, P1 plus T1 goes, and in fact, you're looking at my screen. What we can say is this, if you take a look at my screen, P1 plus P2 plus P3, all 3 of those together will give me my total pressure. Now, in my notes, there's some manipulations of problems that I was going to have Allison do on the board. But instead, I'm just going to show it to you right here because this is going to make it go a little bit quicker and it'll be a little bit easier for us to deal with. Okay, so let's just look at the screen for right now. Would you agree with me that the formula for actually, I'm going to turn to you really quickly. Can you write PV equals nRT somewhere on the board? Okay, if we're isolating P in that formula, wouldn't PV equals nRT, wouldn't it be P equals nRT over V? Can you write that down? P equals nRT over V. Fair enough. Well done. Now, take a look what she has on the screen. Would you acknowledge that each of those pressures, we could substitute in nRT over V for each of those P's?
Yes.
Now, typically in a container, the volume, if they have all the gases in the same container, won't the volume be the same?
Yes.
And if we're in the same container in the same conditions, usually the temperature is going to be the same. And R is a constant. So I have three constants. The only thing that's going to change usually is the number of moles of the gas that I have. So if we substitute out the moles of the gas, and I'm gonna show you right now the stop broadcasting on you for a second. Sorry. And I'm gonna go to screen present. Yep. So I'm going to show you really quickly, just remind you this. So you see how in each of these cases, N1, N2, N3, and you see how that T and the T, the V, and the R are all held constant. So I can factor it out. So N1 plus N2 plus N3 all times RT over V. If I do that, it's going to give me my total N instead of saying N1 plus N2 plus N3. Couldn't I just add up all the moles and multiply by RT over V? And by the way, someone was asking, well, doesn't that V extend all the way down across? Yeah, it sure does, because you're dividing by the whole thing by V. Agree? So watch what I could do. Let's say pretend that Kenna, Austin, and Leo were actually gases, right? If I knew the moles of each of their gases, let's say we had 1 mole of Kenna, we had 3 moles of Austin, we had 2 moles of Leo, right? I could then figure out the total pressure by combining your moles into one single thing. Now, here's why we can do that. Didn't we make this assumption about ideal gases that every gas has a negligible volume? So essentially, all of our gases are exactly the same. So if I have 1 mole of Leo or 1 mole of Austin or 1 mole of Kenna, they're all going to provide exactly the same amount of pressure at the same temperature, and they're all going to occupy the same amount of volume at the same temperature. Does that make sense? Right? So notice in our equation, does it have anywhere in there where it allows us to figure out that one gas might be different than the other? No. The mass in there or anything else? Now, mole-wise, if I tell you the mass of everything, the number of moles might be different. But I want you to look at this because they're going to give you partial gas problems all the time.
Is that like something that we should just like think is always true? That like.
Yep. No, what they typically will do though in problems, they'll actually give you information about like 2 of the gases, and you'll be forced to figure out information about the 3rd gas. Okay. And the way we can do that is by, if they give us the total pressure and they give us the pressure of the other 2 gases, we know what the pressure of that one gas might be, simply by subtraction. Do you guys have me on your screen broadcasting right now or no? Yeah. Okay. Now, I'm going to show you one more thing here, and it's called mole fraction. And can someone else read this? And I'm putting in my note, putting in the notes on the board here, because this is a piece of information that you guys can use to solve problems.
We are always on the lookout for alternate ways to find out pieces of information in a problem. Mole fraction is a way to squeeze extra info out of a problem that seems unwilling to tell you anything more. If the simplest terms possible, mole ratio is the ratio of the moles of one gas to the total number of moles of all the gases in whatever mixture we are dealing with. I'm not going to show the work involved in proving the concept of mole fraction. You can turn to page 207 in your book for that. But I'm going to present the truth here.
Okay, so it's actually not an X. It's a weird, like kind of a weird loop X. That's like a fancy X, right?
That's on this one.
Yeah, and it represents, and I think, let me see if I have it in the other.
It's like an infinity.
Oh, let's talk about it.
Okay, so in the book, there's like 3 different pages just showing you how to get to the mole fraction, and also what's the other one that we do? It's like that one guy's law. What's his name? Well, like it was in the summer reading. It was the
Avogadro's law, Dalton's partial pressure law.
No, it was some other one. But do we need to learn how to like get to the?
Why don't you show me what you're talking about, and I'll tell you what I need to know.
Okay.
Because I don't know at the top of my head, but perhaps. Now, am I still screen sharing here?
Mm-hmm.
Okay. So, if you take a look at this right now, see how the X has the one line is straight and the other X is kind of a looped X down. So what mole fraction is mole of one thing compared to the total moles is equal to the pressure of that thing compared to the total pressure. So watch. My notes do it a little more cleanly than this does. So if I take the moles of one gas and I compare to the total moles, that's going to be the exact same ratio as the pressure of that gas compared to the total pressure. Why does that become a big deal for us? Here's why. Because if I give you the moles of all the gases, so let's say I give you three gases, right? And you get the moles of all three of them. And then I tell you, and then I give you the pressure of one of the gases. Well, if I know the moles of that one gas, couldn't I add up all the moles to get the total moles? And if I have the moles of the one gas and the total moles by adding them up, and you give me the pressure of that one gas, couldn't I then solve for the total pressure? So we're often able to use mole fraction to tell us information about gases that we normally wouldn't get. Now, we're going to do some problems with this, but can you guys lock this into the important equation category of your brain, which, by the way, is the same part of your brain that you should be remembering molar mass is equal to dirty P. Yeah? Okay. Any questions here? Now, let me do this here. Let me go back briefly here. And before I go to any question on this so far? Okay. Before I do that, let's go back to gas stoichiometry. Now, did we talk about gas stoichiometry a little bit at the very beginning? Okay. So let me do this if I can. It's not my notes. It's on page 6 of the other notes. And I want you to turn to exercise 12. I have it on my screen right now. Can you do it on the board for me? Can you write that out? Because I'm going to go back to the board. It should, if you look at click on me, I have it on the screen right now.
Oh,
Okay. Really quickly. Do you see how we have solid? What's that? Someone is echoing through me. What's that? Someone needs to mute. Do you see how we have a solid, and a gas? The screen share is not on right now? Okay, that would explain why. Oh, that's why. Okay, let me try again. So everyone was just looking at me during that time. All right, let's take a look at this. So if you take a look at this equation, you see how we have a solid here, and a gas. So if I want to, I can use gas info for the CO2, but I certainly can use PV equals nRT for either of these two right here. Would you agree? So I can use moles to go back and forth between any of these. Don't they give me grams of CaCO2, COCO3 in this problem?
Mm-hmm.
Yeah?
Yeah.
So if they give us grams of that, and then don't they give us a bunch of information about CO2? Normally in previous problems, when they give us grams of everything and we convert to moles, but can't we use Pivnert to move back and forth between moles as well? I want you really quickly to do this problem on your own. I want you to try and do it on the board, and I'll come back to you. I'm sorry? Or Google.
Google. What is it?
100.0. Wait, you mean like
It's like 100.09. Yeah. You want me to kind of walk you through this? Okay.
Wait,
So I'm gonna look. Can you guys see my screen right now or no? Yes. You guys see my screen? Okay. Watch. Don't they give me 152 grams of this solid over here, CaCO3?
yes, sir.
Now, if they give me grams, almost automatically, my first instinct is to do what? Convert to moles, right? Because if I have moles of this, don't I really know what the moles of these other two things are going to be or should be as well? Because isn't it a 1-to-1-to-1 ratio? Aren't they asking me information about CO2 though? So if I know that how many moles I have of CaCO3, I know how many moles of CO2 I have. But don't they telling me that my CO2 is at STP? And what are they asking me to solve for? The volume. Can I tell you there's two ways you can do this? There's the fast way and there's the not so fast way. The fast way is simply this. Don't we know that 1 mole of any gas at STP is 22.42 liters?
Yeah.
So if I know my moles of CaCO3, wouldn't I know my moles of CO2?
Yes.
If I know my moles of CO2 at STP, couldn't I then use the conversion 1 mole per 22.42 liters and figure out the liters? Now,
Wait, so that would be what?
that'd be the easy way. The long way, you know what you do? Pivnerd it.
Yeah, I just saw.
You're going to get the exact same number. And by the way, this is one of the things you need to realize. There's always more than one way to solve these problems. Now, I don't know which way you did. You Pivnerd it. So Pivnerd is a completely equally good way of doing it, just longer, right? Because don't they give us the temperature and the pressure? And don't we have the moles? That kind of feels like 3 of the 4 variables, doesn't it? So I'm guessing, Leo, did you do Pivnerd in that one as well? Now, the only thing that you lost in that is time. And let's be honest, on an AP exam, time becomes kind of an issue for us. But other than that, the problem is still good. Okay, I want you to do the next problem. Now, yes, sir.
What are our significant figures for SC?
Oh, that's a good one. I think it's exactly 1 atmosphere. And the unfortunate thing is that the temperature is actually 273.15. And I think there may be more numbers after that. So at best, I think you
just went to 3 sig figs because they didn't.
They did it at 273, right?
Because I think they just went to 3 sig figs because they gave you 152 grams, and so they just went off. And they didn't like.
So
exactly 1 or 273.
You're going to find in some problems, especially if they're doing like a lab-esque problem, they'll probably give you more significant figures on the 3 at the beginning. And that's when I would use 273.15. I guess we could look up more, but I think even on the cheat sheets they give you, I think they give you 273 Kelvin. I don't even know if they give you 273.15 on the AP exam.
So don't use the 1 ATM as your.
No. That we'll have to treat that as 1.00 or whatever.
Just like 1.0 infinitely.
Infinitely.
Yeah. So that's never your.
That's never going to be your stopper. Okay. Now, can I point out this to you? Let's look at number 13. And can I remind you that in order to do any problem where you are reacting something together, mustn't you have a balanced equation in order to do this? And lest you get really confused here, don't they tell you all the main ingredients in here? Methane gas reacting with oxygen to form what? Carbon dioxide and water, right? Now, super fun fact. You kind of need to know methane's formula in order to be able to do this, right?
CH4.
It's actually CH4. And if you need to remind, we're going to go later on in the year when we talk about organic chemistry, we're going to do some naming, which we call nomenclature. Do you remember how we did in pre-AP, we did many peanut butter, methane, ethane, propane, butane, and then we went pentahexaheptaoctanonadeca, right? If you know the number of carbons, you can double it and add 2 to get the number of hydrogens. So start with CH4, write your balanced equation, and I want you to solve this. I'm going to give you guys about 3 minutes to do this, please. You're going to be like guinea pig on the board here. I think you're good there. Anyone stuck?
A bit.
Okay.
We're using Pivner to solve this, correct?
You're going to have to use some of Pivner. Yeah.
Okay, good.
Maybe a lot of Pivner.
That's what I.
And by the way, do you see how they tell you that's methane gas? And then don't they give you volume, temperature, and pressure? Can you do me a favor when you're doing any of these problems? Can you lock into your brain PV, N, and T are the 4 variables we're going to be using all the time? So they give you 3 of those variables, and you're like, where do I go next? It's probably that 4th variable. Plus, aren't we dealing with an equation?
Oh, so we're just gonna
So you're going to have to find the limiting reactant. You're going to find what the moles are of each one, right? Figure out the limiting reactant and go from there.
Keep forgetting on it.
Point zero. Go ahead.
0.08206.
You're
You got a well played there. See, she came to your defense. That's very sweet of you. Excuse me.
Anybody else get 24.45
No, you multiply things together, but now you have to divide by the liters times the pressure.
I did. I think it was just like,
But that still should not put you that far off, all right?
It doesn't do like the order of operation. I can't like divide by it.
Oh.
Like,
Yeah.
so.
Yeah, I got 5 points.
I mean, like I just ordered. Is it 5 point? Is it 0 point something? It's just that.
Wait, Leah, why did you get that?
Wait.
Okay,
Wait, don't go yet. 'Cause I think
we don't have a ton of time, and I want to make sure that we get the last section here on how to do a gas problem.
Got it.
Okay. The really important thing is you have the equation written down, and I'm going to quickly go over to. Actually, I'm not going to switch over because I don't want to. All right. Will you acknowledge that you have to have a balanced equation first, right?
Yes.
And if you take a look at what Allison has on the board, it is a balanced equation. Then they give you information to figure out the moles of methane. They give you information to figure out the moles of O2, right? I'm hoping that you guys are doing the shortcut way of figuring out the limiting reactant by dividing by the coefficient. What do you end up with as your limiting reactant?
CH4.
CH4. And you know the number of moles you have of that, right? So if you know the number of moles of CH4, can't you then figure out the number of moles of CO2? Because isn't it the same?
Yes.
And if you know the moles of CO2, don't they give you other information there to solve for the volume?
Yes.
And solve for the volume. And they give you the volume in the equation. Now, this is the last thing I'm going to teach you today, and I want you need to look at the diagram I'm showing on the screen. So look at water displacement, and I want you to glance at this for a minute. I'm going to explain it to you because this is one of the types of problems that students typically stumble over, and it does not have to be that hard. Everyone looking at it?
Yes.
It's on my screen, but it's also on page 9 in the bottom of the page. Okay, so one of the problems we have is this, and by the way, the reaction that's going on here is we're taking KClO3 and we're decomposing it, or we're breaking it apart. Does KClO3 want to break apart, do you think? No. So there's two ways we can help it. One, do you see how we're heating it? And two, do you see this MnO2? This MnO2 is actually called a catalyst. And what catalysts do is they help reactions along that normally don't want to go. The actual reaction itself, if you want to write it right underneath it, is KClO3 breaks apart into KCl plus O2. Thank you so much, Allison. KClO3 breaks apart into KCl and O2. And if you balance that, I believe you have to put a 2 in front of the KClO3. Actually, I have it right down below here. So 2, 2, and then a 3. Now, why am I telling this? And why are we going to gather oxygen this way? Would you, if you take a look at the equation right here, down below, if you're looking at it, isn't KCl3 a solid and isn't KCl a solid? O2 is a gas, right? So if I just sat this on a beaker, if you take a look at me, if I put it in a beaker on a hot plate, right? And I put KClO3 in there with the catalyst, wouldn't KCl start to form and wouldn't O2 be generated? Wouldn't it just leave? Where would it go? Everywhere, right? So we have no ability to collect it. So what we do often is we collect underwater. Now, see this container right here that is half full? That started off as all the way full. And you remember how we can burp water?
Yeah.
So if you take a full container of water, right, fill it all the way up, and you set it into water, right?
With a gas tube.
Right, with a gas tube. And the way you can get that is you realize if you tip a container under water and let the air out, you get only water in the container, right? Then you see how the reaction is actually occurring in the test tube, but we have a tube that goes in and it's directly in the water of the container. Now, what happens is the water gets pushed down. So the way of the water is going is down. So the gas is pushing it down, right? And what we can do is we can trap all the oxygen that's generated inside this space right here. Can I tell you a problem?
Yeah.
When we do that, water molecules or water vapor, gas molecules, they get bounced off of the water and they start bouncing around in here as well. So if we were ever to measure the pressure of the gas inside this container, it not only has oxygen in it, it also has water in it. And that's problematic if we only want to figure out the pressure of the oxygen. So in every problem, are you all listening to me right now? In every problem where you're dealing with water being or gas being collected versus water displacement, in other words, do you understand displacement means taking the place of water? So you had water in this container and gas is taking the place of it. That's why we call it water displacement. They must tell you the water vapor or the amount of gas at that particular temperature. So we know at a particular temperature what the water vapor is going to be, which incidentally, that actually happens. I mean, in Houston, we have tons of water vapor in the air, don't we? I mean, it's so ridiculously humid. So we get a particular temperature typically. Now, there's other conditions that impact us, but temperature impacts how much water can stay in the air. I don't know if any of you guys ever traveled to China or Hong Kong.
Yes.
Okay, so I don't know if you had this experience, but for us, we would hang up our clothes to dry, and it was so humid that it wouldn't dry. We actually were in our room, and it was raining. It was misting in our room because the air was so thick. It was above 100% humidity. Now, why am I telling you this? Because watch, in every scenario, if they're ever asking you to figure out the amount of oxygen or whatever else, take a look at the actual problem here. They will always tell you, do you see where, look in the next problem? He just says, and the vapor pressure of water at 20 degrees Celsius is what?
Oh.
21 torr, right? So if they tell you that the total pressure is 754, that's including the water vapor. So if they ever want to figure out, information about the gas itself, do you realize you're gonna have to substitute that out? Now, right now, I want you to start setting up the problem in exercise 8. I don't think you have time to finish it, but set up the problem in exercise 8. Ignore the fancy words or anything else that are in that problem because it's a very straightforward problem.
What is the NRT problem? Or a ideal
I'll let you figure that out.
Hold on. Are you going to the bathroom?
Sure.
Well, actually, we have 2 minutes.
You literally do have 2 minutes, but yeah. By the way, just for those of you who maybe watch this later, if you want to remind yourselves, there's 2 worksheets over there that I asked you guys to pick up when you came in the classroom. If you're not, they're over there. One's called Really Cool Gas Problems, Really They Are. Your homework tonight is going to be problems 1 through 10. I don't want you to do 11, 12, 11 through whatever, 15 or 16, because those become a little more rickety problems, and I want to be able to watch over your shoulder while you're doing them.
Are we doing both for homework?
No, literally only problems 1 through 10 on the some really cool gas problems. So I'm going to stop the.
So would you subtract 21 torque from 7 torque?
What's that?
Would you subtract the?
Yeah, if they're trying to figure out the individual, if you're trying to figure out the individual, yeah.